Hi, this is Randy May with Tolerant Lab in the US. Thank you for coming to my session and hopefully learning a little bit about stream processing and Hazelcast Jet. So first we're going to talk about what stream processing really is. I've got quite an echo here. And then we're going to talk about, that's better. No, still there. Just one second. Okay, that's better. So first, we're going to talk about just what is stream processing in general, and then we're going to talk about specifics. There's a new category of product that are stream processors. So stream processing problems aren't brand new, but stream processing products are pretty new, and they're exciting and interesting. And I'll share a little bit about that, and particularly about Hazelcast Jet, which is a stream processor from Hazelcast. So why is stream processing suddenly a thing? And why is Internet of Things suddenly a thing? Well, over the past years, we know that virtually everything has an IP address now. It could be your lamp or just your car or your bicycle. Anything could have an IP address now, and it produces information. And people generally want to derive insights from that information, especially businesses. And we're going to go over some examples, but that's really what's driving this is basically Internet of Things produces a flood of data, and companies want to process it and make sense out of it. So, and like I said, this isn't new, but stream processing solutions are new. So Hazelcast Jet is the one that I'm going to talk about today. And it's built from the ground up to basically handle a flood of information and a flood of events, and then to help you drive insights without you having to write aloud the plumbing. So it's pretty cool, and we'll look at some code toward the end of the presentation. So let's first spend a few minutes talking about what is stream processing, because it is different. So here are the two, I would say probably the two top vendors and what they say about it. So Hazelcast says stream processing is a practice of taking action on a series of data at the time the data is created. And Ververica says stream processing is the processing of data in motion, or in other words, computing on data directly as it's produced or received. All right, so let's use a problem to think about why you'd want to do that, or when you would want to do that. It's obviously not everything is a stream processing problem, but our example is definitely a stream processing problem. So let's think about any enterprise where the administrator needs to digest all the logs and the health metrics off of, say, a server farm, and then to drive insights. And in particular, let's think about the administrator wants to calculate a rolling average of response time over the past 24 hours, and then to detect any response that is, or any interaction that's at least 10% over the response time. So how do you do that? And let's just look at two different approaches for doing that. So, okay, so one way to do it is to take all those events, use some kind of ETL, whether it be streaming or whether it be batch, and land them into a data store like a data lake or a Hadoop or whatever it is, and then repeatedly run queries so that you can compute the average or the rolling average over the last 24 hours, and then also detect those interactions that are more than 10% over. So that is one way to do it. The other way to do it is I obviously picked an event processing problem, or a problem that's appropriate for event processing. The other way to do it is on the fly, right? So what we could do is we could take all those events, ingest them. If they all look different, we might transform them to some standard format, And then if we had the right machinery, we could compute windows on the fly. If you have different classes of servers, some web servers, some app servers, you might want to compute different windows for different classes of servers. Because at some point aggregating totally different servers together and computing the response time over the last 24 hours might not make sense. So, then look at window by window, compute the aggregate, then filter all the events and look for events that are that exceed the 10% threshold, and emit notifications if need be. So you could certainly design this problem as a series of steps. And let's look at the trade-offs between a series of steps that are acting on the events as they occur. And you need to keep state, right? So you need to, for example, you need to keep the last 24 hours of responses so that you can constantly produce the window. You don't have to store everything, but you have to somewhere store the last 24 hours so that you can compute the average over the last 24 hours, and so forth. So there is state involved in this. All right, so let's look at a comparison of these two approaches and think about what happens. So one thing is just getting the data landed in the first place can take time. So in a more conventional or database-based approach, the data you may have more latency, or the data may be less fresh, is what I was trying to say, because it may take hours to get the data landed, or even minutes to get the data landed in a database, whereas the stream processing system already has it sitting there in memory. Latency-wise, it's probably also going to be faster for the same reason. And then one of the most important reasons why this is not a good problem for like a database approach is scaling. So as you are landing more and more data into this data store, the amount of data you have to search through gets bigger and bigger and bigger. So it doesn't scale very well. The approach doesn't scale very well for this problem. Whereas stream processing, it can be broken out, and different servers can process events from a different subset of your infrastructure, and it's very parallelizable. So again, stream processing is more appropriate. And the other thing is, do you really want to store all that data? Maybe you do, but maybe you don't. Maybe you don't want it at a minute by minute or second by second granularity. Maybe you need it to do this computation and raise the alerts, but you don't need it. You don't need to keep it around forever. So that's another potential advantage of stream processing, is it doesn't have to store all the data. In fact, it can help you with that problem, because the stream processor can compute aggregates, and you can store those instead. So for some problems, stream processing just makes more sense. And we've been doing things, probably I didn't tell you anything you didn't know. We've been doing things like this for a long time, but what's new are these engines and infrastructures that can help you implement stream processing solutions. Okay, so let's look at some use cases that are interesting. I'm going to talk about stream processing use cases, and then talk about how stream processors, and in particular Jet, works. So really, any time where you have events and you want to derive insights, it could be a stream processing problem. So fraud is a good example of a stream processing problem. So we all know when you swipe your credit card, that generally comes back pretty quickly, and generally somebody somewhere has actually done a fraud check, which could even involve running that transaction through a machine learning model that takes into account the nature of the transaction and also information from your account, and comes up with some kind of yes or no, or likelihood of that this is a fraudulent charge, and they're pretty good. So and they're fast, right? They need to be fast. There's another one that I worked on that's very similar, check deposit risk, where when you deposit a check over your phone, depending on a lot of factors, it might say your money's available now, or it might say your money's will be available in a week, or some split, and that has to be computed on the fly. So perfect stream processing problem. Another one that does happen is that large enterprises watch access to their internal networks looking for bad actors. So you can look at the logs, the access logs on all of your servers as event sources. So you can feed those. So if those are the events and you feed those to a stream processor that is running potentially a machine learning model to basically, it might not be looking for some specific access to some server. It might just be looking for something that meets some definition of unusual. So again, it's clearly, you want to derive this insight, as fast as you can, because, you may be able to detect an intrusion or, more rapidly. So that's a good stream processing problem. Okay, fleet surveillance. This is another one that I think is very interesting, and we're going to go through an example of how you would implement this in Hazelcast Jet. So if you have a fleet of vehicles, of course, they produce data now. They're not just dumb vehicles. So they produce GPS pings, and they produce also telemetry about what's going on in the engine and all sorts of information that could be useful. So people that operate fleets want to digest all that information that's coming in and derive insights. And the insights could be just simple as, where's my truck? Or it could be, is this truck on its planned route, or is it way off? That could be something that you want to know about. Do the engine trouble codes indicate a breakdown, like maybe the airbag deployed? You want to know about that, right? So stream processor can handle that whole flood of data off of your fleet, and with your run your business logic to derive insights. So another good example. Okay, machinery monitoring and preventive maintenance. So I know customers that are doing this as well. So if you have a shop full of equipment, again, those things are instrumented, and they can tell you, what temperature certain parts are and the RPMs and things like that. And you want to monitor that information in order to prevent breakdowns. So again, the events are, in this case, are telemetry off your machines. And the insights are just basically anything that could indicate that something is broken or about to break. Using machine learning for predictive maintenance is a big thing now. So, I just wanted to mention, while we're talking about machine learning, one of what I've seen in the past is one of the places where data science projects can break down is operationalization. So they might build a model that can, for example, predict failure or predict fraud or whatever it is, which is great. But then those models have to be insinuated into your regular business system some way for them to be valuable. To actually derive the insights, they've got to be connected to the real stream of data that's coming into your business. And that's exactly what stream processing systems can do for you. Another example, I think this one's cool, interesting to me at least, business process monitoring. So you may have an up and running business that's got, it's got all sorts of business processes, and you may have all sorts of business policies, and you may not really be sure if you're meeting your SLAs or not. If a customer places an order, has it been picked? Has it been shipped? Did anything fall through the cracks? So you can actually look at your whole business as an event source, and you can have a stream processor watching all those events and making judgments about whether you're meeting your SLAs and whether your business is running the way you want it to run, and detect situations where it's not. So again, stream processor is providing the plumbing, you provide the actual algorithms and conditions to do that. Okay, so that's another good stream processing example. Market sentiment analysis is another one. I think this is pretty intuitive. So if you launch a new product, or you launch it into a new market, then you can potentially harvest social media. All the platforms actually have APIs where you can get tweets and you can get posts, and you can run those through a machine learning algorithm that detects sentiment. We like it, we don't like it, and so you can quickly get feedback on how your new product launch is doing in a certain market. Once again, the event processor, the stream processor, is providing kind of the platform for doing that. Okay, so hopefully those are some interesting examples about what people are doing with stream processing today. Now I just want to talk about how does Hazelcast Jet do stream processing, and then we'll actually look at some code. So you could get an idea of how easy or hard it is. So the model that Hazelcast Jet uses, and as far as I know, most stream processors is they have you take your break your task down, or sorry, break the what you're trying to do down into tasks, and the tasks, like in this case, it's just a single sequence of tasks, but it could fork, or it could join. You could pull in data from. You could, for example, augment your events with reference data from your database. But basically, you model it as a sequence of tasks, and then the job of the event processor is to run it. So here is an example of word count. Word count is kind of the hello world of event processing. So I would say don't worry at this point too much about the code, because we're going to come back to the code later and do a deep dive on it. But basically, what you can probably see here pretty quickly is there's correspondence between this graph with the blue circles and the code. So I'll define a source, and then I'll define a mapping operation, which is typically going to transform the format. And I'll do formatting. I can do aggregating, and then I define a sink. So that's kind of the model that you use. And what I'm showing you isn't just sort of a snippet. This is everything. So word count's not that interesting, but the point is you could actually scale it up. And you could scale it up and run it on 100 nodes and have it be fault tolerant. And this is still all the code that you would need to write. Okay, so what Jet does is Jet takes your graph, or your pipeline is what we call it. Jet takes your pipeline and it deploys it at runtime. So basically, each task is associated with an outbox. I'm sorry, each task is associated with an inbox, and each task, pulls from its inbox, does what it needs to do, and then forwards it on to the outbox. And many of these operations are parallelizable. So Jet will not just deploy one single instance of your source or your map step or whatever the step is. It'll deploy multiple instances, both within a server and across servers. Then if we're looking at word count or something like that, you could have, say you just split the corpus of text line by line and sent some of the lines to one server, some of the lines to another server. And each server independently does a word count. That's fine and that's smart, but you still have to aggregate it. So you can see here this step in the middle. So Jet is smart about doing things like that. So it's got a lot of optimizations. There's a way for you to tell it how the job should be parallelized, and then it's smart enough to send everything related to a certain key to the same node, so that your final totals will be correct. So I've put a link in the article here. I'll put a link in the presentation here about the technical details of that. It's pretty interesting reading. Pretty cool stuff. Okay, so that's a little bit about how Jet actually deploys your job and runs it. So let's think about fault tolerance. So things that are stateless are easy to make fault tolerant, right? But this is this is stateful, so that's what makes it hard. What's the state? It's like the state is like the inbox for every single task is part of the state. Another part of the state is when you're filling a window, or maybe all the events in the last hour, and when you're filling a window, that window is state. And there's a lot of other things that could have state. So what Jet does, Jet rides on top of in-memory data grid, which is another Hazelcast product you may be familiar with, and there's other sessions about that. But Hazelcast provides distributed in-memory data structures that themselves are fault tolerant and scalable. So your state all goes down into a Hazelcast map. And one of the smart things they've done is every time the state changes, they don't save it, because that would eventually become a scaling problem. It would limit your ability to process events. So instead, what they do is they periodically take snapshots of all the state, of all the tasks, and they do it in a way that provides you with a consistent cut of the state at a certain point in time. Then if there's ever any failure, the whole process just automatically restarts from the last snapshot that was saved. And it's a pretty cool mechanism. And in fact, that's the exact same mechanism that you can use to shrink and grow the cluster. So if the cluster size changes at all, what happens is it just simply reallocates the tasks so that they are now running on more nodes, and it restarts from the previous snapshot. So pretty cool. That's a little bit about how Jet does stream processing. Now, the next thing that we're going to do is we're going to look at the actual code. So this platform, that we don't really want to do video or live demos on this platform, but you can actually get all the code for this and check it out yourself. This is the GitHub URL. And at that URL, there's both a Vagrant-based version that you can run locally, and there's also a OpenShift-based version that you can run on an OpenShift cluster. So if you're interested and you want to see some sample code and how you deploy it and run it, go ahead and check that out. All right, so here is the system that I want to spend the rest of our time on. It's basically a GPS tracking system. The events are GPS pings. And in the demo, there's a Microsoft data set called the GeoLife data set. And that's what's used in this demo. So basically, if we imagine a system without a stream processor first, you certainly could, you certainly could, for example, send all the events to a Kafka topic, and then basically process those and display them on a map without any real processing at all. And so here's a picture of what that looks like. So basically, the map is constantly updated as things move around, but their events are just flowing through a Kafka topic. There's no real brains in there. So next, we're going to add logic to basically look at each one, or sort of source by source. Like, think of it as cell phone by cell phone. We're going to independently keep track of the speed of each cell phone, and we'll do that by taking a window of time, a small window of time, and seeing how far the person traveled in that window of time. So I've got the GPS coordinates now. I've got the GPS coordinates 10 seconds from now. I can compute your velocity, and then we'll take that information and we'll categorize it. And so that's kind of a rough way that you can figure out mode of transportation. And you've probably seen this, and so Google Maps, for example, seems to know if you're in a car or if you're on the subway or if you're walking. So this is a useful thing. So we're going to look at what it would take to do something like that in Hazelcast Jet. Okay, so the system that we're going to build is going to look like this. So we're going to have the same event stream, but in addition to the UI server, the Boca server, listening on the topic, we're also going to have Jet listen on the topic, and then Jet is going to do some classifications. It's going to split. It's going to basically establish an independent stream per phone. It's going to do the processing it needs to do to categorize the velocity, and then anytime the category changes, it's going to publish an event back to a different Kafka topic, and then we'll use that to update the UI. So this is what the code looks like. We're going to go through it line by line. You know, if hopefully this is of interest to you, but if not, the big takeaway here is that's pretty much all the code. All of this code is very much related to the business problem, and none of it is really related to plumbing. So, and that's pretty much all the code you need to do the job that I just described. So let's look at it line by line. Okay, so I start off and I define a pipeline object. And that's just the container for my directed acyclic graph that I'm going to put the tasks into. Okay, and I define a couple of sources, and in this case, all right, I define a source and a sink, and in this case, they're both Kafka. So Jet comes with connectors to sources and sinks for a lot of different standard technologies, so that you can, and then you can also write your own as well. So I define a source and sink. So the main thing I'm doing there is I'm passing in properties that just allow me to connect to Kafka and find the topic. So Kafka source and Kafka sink defined. What's next? Okay, so now I need to ingest the events. So that's what this looks like here. So pipeline read from Kafka source. I think that's pretty intuitive. And then with timestamps, let's talk about that. So in any stream processing system, you can't assume that the order the events arrive at the Kafka topic or at your stream processor is really the actual order that they happened in. And for many kinds of processing, you need to get them in order. So how do you do that? Well, basically, you have to tell the stream processor where the timestamp is. So if the timestamp is somewhere within the message, you can tell it. And now in Hazelcast Jet relies heavily on functional APIs. So hopefully you're familiar with the Java functional APIs. But anyway, what you're doing here is you're saying for each entry, you're going to call entry.getValue.time, and that's going to be your timestamp. This last part here is a window. So I have to there has to be a finite period of time that I buffer up events waiting to put them in order. And so basically, if an event, so this is 10 seconds. So if an event arrives, 10 seconds later than all the other events in that batch, then it'll be rejected with a message. But anyway, this is the mechanism that you tell Jet how to put the events in order. All right, so now what I have is so you can tell here, the stream stage, that's kind of telling me what is output. And what is output is a map entry with an integer that's identifying the phone. And then you can just think of this as the actual GPS information. Okay. So the next thing that we're going to do is we're going to define our window. And to do that, there's just a built-in primitive. But first, you don't want to create a window of all the events from any phone whatsoever, because remember, we're trying to compute the velocity for each phone. So first, we're going to split the stream, and that's what this grouping key does. So I take the previous stream stage pings, and I call this grouping key method, and I say, and again, it's functional. So I say, take the entry and call entry get key. That's the grouping key, which in this case is the phone ID. So after this call, I've got a parallel stream, one for each phone. Okay. And then on those parallel streams, I define a window, and the window is going to be, in this case, 30 seconds long, and I'm going to recompute that 30. So it's going to look back 30 seconds. I'm going to recompute that window it's going to slide forward every 2 seconds. So, so the output of this stream stage are basically windows. So, okay, so let's go on to the next stage. What am I going to do with those windows? Okay, so Hazelcast lets you define your own aggregator. And in this case, what I really want to do is I really want to look at the beginning and the end of the window. There's a GPS coordinate associated with the beginning, a GPS coordinate associated with the end. And I want to do some spherical trigonometry to figure out the actual distance between those two GPS coordinates. And then I'll use that to come, and that along with timestamps gives me the velocity of that particular device. So that is not obviously that's not a standard aggregation. It comes with some standard, if you want to just compute a sum or an average or something like that over the window, that's a standard. But if you want to do something else, that you can just do that. And again, very, very heavily reliant on functional APIs. So what we're going to do is we're going to define our own aggregator, then we're going to put it in the pipeline. So here we're defining our own aggregator. And what we're doing is we're saying, let me go back. We're saying the create function is velocity accumulator. Okay. And then the and accumulate function, which is the event by or window by a window function, is this one here. So I'm going to define a function that takes a velocity accumulator and event, and I'm just going to take the event and pass it to the velocity accumulator accumulate method. So what's in there, that's up to you. You can do whatever you want, and the method doesn't even have to be called accumulate, right? That's the good part of the functional API. You don't even have to implement it. You don't even have to implement a interface. Okay, and combine. So since it might have taken the stream of pings from different phone or from the same phone, and potentially they're in different, even possibly on different nodes or at least on different streams, they eventually have to be combined. So how do I take two accumulators and combine them? Okay, and then finally, how do I get my actual result, which in this case is the distance between the two. So I provide functions for each of those operations that the jet engine might have to do, and that's my aggregator. Now I just put it in the stream. So I take the ping windows, and I say aggregate, pass it my velocity aggregator. Okay, so now I am producing these keyed window results. What these are is basically every single window, which was produced every 2 seconds. So I'm already kind of thinning out the event stream, right? So every single window, it's gonna have the ID of the phone, and it's gonna have the velocity as a double. So it's just going to be constant. That's what's going to be on the. That's what this stream stage is going to emit. Okay, so we're almost there. Now we've got to do a couple more things. One is I just need to categorize it, right? So that, and the other thing I need to do is I want to filter out no changes. So most of the time, remember these windows are being produced and evaluated every 2 seconds. Most of the time, my category, whether it's, bike speed or walking speed or car speed, most of the time my category is going to be the same between two windows. And there's no reason for me to constantly emit, okay, it's, we're going to color code it. So there's no reason for me to constantly emit, it's blue, it's blue, it's blue. I should only emit an event when it changes. So this is how we can do that. So the step is called map stateful, and you can see that it returns a 3-tuple. That's the phone ID. That's the current velocity categorization. It's going to say something like red, green, blue, and we're just going to use colors for categories. And then this is the previous one. So it's a simple little. So I have this ping state object that I'm using in my map stateful operation. And I just put this in a jar and send it to the cluster. And what it does is it first instantiates an instance of my ping state, and then it passes every item to it. And in particular, it's passing it to the update method that I wrote for this. And the update method is just going to it's just going to categorize it red, green, blue, and so forth. And it's going to also remember the last value as well. Okay, so anyway, now I'm emitting these 3 tuples: phone ID, old and new. Okay, and then last thing I need to do is filter out the no change. So very simple. There's a built-in filter step, and I don't provide an object, I just provide a function. So I take this categorized velocity stream stage, and I apply a filter to it. And the filter does this. So basically, if item.field1 does not equal item.field2, then that's an event I'm interested in. Okay, so now the type is the same as before, but I'm only getting change events. So, it changed from it's phone number 5, it changed from red to blue, something like that. Okay, all right. So then lastly, I just need to send those back out on Kafka. So when I do that, what I get is I basically wrap that all up in a jar. I deploy it to Jet, and Jet then, like I said before, it deploys it to a cluster of any size, and it runs it. And the Jet Management Center shows you something that looks like this. This is a snapshot of the Jet Management Center. And if you click on these boxes, it'll give you statistics about events in and events out and things like that. And so finally, what the whole solution looks like is like this. So now I'm not only seeing the events I'm not only seeing all the individuals moving around and where they are, but I'm getting a velocity categorization, which I'm representing with colors here. And that's something that Hazelcast Jet can easily handle thousands and thousands of these, and even do a pretty heavy calculation like the spherical trigonometry I was talking about. And do and handle that no problem. So hopefully that gives you a good idea of how Hazelcast Jet, of what is stream processing, and how Hazelcast Jet can enable you to basically write a pretty complicated pipeline without, with just focusing on just the business logic. It's a pretty cool product and a pretty cool field, I think. So I hope you learned something, and thank you very much for your time. I'll be going over to the chat room.